Hello, everyone. Welcome back to SAT Math Question of the Day. We have where we tried Brothers Chaiken. We're brothers from birth, and we try to show you different approaches for studying for the Math SAT and also approaches on doing specific SAT math questions. In terms of studying for the Math SAT, pretty good way of doing it is to take the Khan Academy courses. You just Google Khan Academy SAT practice, and you could do the non-digital SAT practice or the digital SAT practice course. What's nice about Khan Academy is they've partnered directly with the College Board, so these courses go over the material, the exact material that is on the SAT. So what we do is we go through the we're going to cycle through all the topics. We're going to cycle through all the problems. We're only going to do the advanced questions with the idea that if we hopefully go over how to offer approaches and how to do the advanced questions, then you could use those approaches to do the mediums and the foundation. So we are here now at advanced math, and the other day we did quadratic graphs advanced. So now we're doing exponential graphs advanced. Exponential functions are a very important type of function. They are a function. And if anyone's lived through COVID, that describes COVID, exponential growth. Okay, so here we go. We are going to do the first question today. Let's go, as they say. We got a little bit of a problem here because we have to fit everything in one screen. So, Seth's not going to like this because he was complaining about his eyes. Ouch. Well, why don't we read the question and then we'll look at the answers, okay? So, f of x is 2 to the x power minus 1. We'll go over what an exponential function is when we go over the answer. The function f is defined by the given equation. Okay, fine. Which of the following is the graph of f of x minus 2 in the xy plane? Okay, this is really more of a question of transformation of functions, which we didn't really see too much on the non-digital side of the SAT. This is really a question of transformations of functions as opposed to exponential functions, because it doesn't really matter what the function is. If you have a function f of x and you want to see what is f of x minus 2, if this is the graph of f of x, then f of x minus 2 takes the graph and moves it 2 in the horizontal shift. So you go 2 here, you go there, and as long as this is a 2, then you have it. Okay, so
when you go from f of x to f of x minus 2, you take the curve, and then you take the curve, shift it to the right.
Yes, horizontally. Horizontal shift.
Yeah, to the right. To the right.
That way.
Not the left.
Way. Yeah, that way. Yeah. I always get it wrong, but I have to.
Now, okay, so approach number 1, which is the approach that I took when I first saw the question, is to apply what I wrote in red and what Joel said in green. Apply that rule.
Yeah.
A way to memorize it is that it's a little weird.
I agree.
When the shift amount is written with a minus, you take the curve and shift it to the right in the positive direction.
Right, yeah.
Even though it's a minus.
Yeah.
Okay. Now, approach number 2 leads us to understand why this strange-looking rule works. Okay. So here is the answer gotten from let's see. It's right.
So
yeah. Here's the
why don't we do
answer that was gotten. Let's see. 2 to the 4.
Hold on.
No.
Wait. Come on, Seth.
Okay, okay. This
Let's
is
be organized.
okay. Hold on a sec. Hold on a sec. This is the answer. Uh, that wait, when x is equal
Seth,
to
please, come on, stop. Let me just finish. Before you go over that. Before you go too much into detail, the problem now is we have this thing. What's going on here is what we said here has nothing to do with exponential graphs.
yeah.
Nothing to do. The problem is that they never gave us the graph of f of x. They only told us what f of x is. They didn't tell us. They didn't do the graph of f of x, which means we have to graph this. That's where the part of the exponential functions comes in. So we can also use, we have to know something about graphing exponential functions, and then we also do translations. F of x, if it starts out as 2 to the x, we can graph 2 to the x. 2 to the x, when x is 0, then y is 1. So it sort of like goes like that, right? But it's a -1, which means we have to, it's a -1 outside. So we actually have to translate this thing down 1. So to a certain extent, this is what, we'll put it in big blue, okay? Big blue. Now don't forget, you have a graphing calculator. So that's f of x. So which of these looks like it's moved over 2 units? Which one looks like it's moved over 2 units? 2 units. So this would be, that means it would have to go through 2, 0, right? It would have to go through 2, 0. So the only one that goes through 2, 0 is Seth. Wow, Seth got it right. My God.
Yes, I did. Okay, you know, I told you the way I saw this. What I did, so my second approach was I saw this exponential.
Yeah.
And I know what I saw from this is that when x equals 0, we get 2 to the 0 minus 1, which is 0.
Right.
Right?
Right.
So I also recognize that this is a case of the kind of exponential that goes through 0. So it rises fast out of 0, and then it slowly falls and is asymptotic to the constant. So I looked at the equation. I looked at this original function f, and in my mind I said f is this. And then I saw that they were asking us to shift it to the right 2 steps. I realized that when in the original f, when x equals 0, the function value is 0. So I knew it went through the origin. And so what I did was look for what Joel said, the one curve for which when x equals 0, the curve, when x equals 2, the curve equals 0. So this is the only one which goes through the point x equals 2 and y equals 0.
Right, so that's more of a, this is something to note. Since we've been doing the first question of all these topics, this is the second question we've seen in like the last 2 weeks, which requires you to either do it the way Seth did it here or to use transformations of functions, which is, what are they telling us? They're telling us it's important to know how to do these problems either the way Seth did it or using transformations of functions.
Now, there's another approach, a third approach, and an issue with this problem.
Yeah.
Again, I'm going to write what they wrote. F of x, okay, is 2 raised to the power of x minus 1, right? Well, they're asking us about questions of f of x minus 2 and what the curve of that looks like. That is a curve, a y of x.
Yeah.
Okay, here's the big issue. The x here, this is the first x, and the x here, they are completely different symbols.
Yes.
They
yes.
are used for completely different applications.
Right.
Either one, this one could better have been written f of t
right.
equals 2 to the t. And then the curve that we're interested in, as x varies, would have the formula 2 to the x minus 2 minus 1. So we're interested in this curve as x varies. So another approach is to say we're interested in y equals f of x minus 2.
Yeah.
So what is, and this function of x, what is that? F of x minus 2 is 2 to whatever in the parentheses.
Yeah.
Which is x minus 2. X minus 2 is the exponent, and the exponential has a 1 subtracted. Right. So the third approach is to calculate the composition function.
Right. Yeah. Which I did.
And then look at this expression and see which curve describes it.
Right. Yeah, and I did that at the bottom. While you were talking, I realized what you were doing, and I actually went over here. It turns out to be -3/4. Well, we could go over it a little slow. You want
So let's approach this. An easy thing to do here, it's easy to exponentiate when the exponent is 0.
Yeah, certainly.
So we figure out that when this x equals 0. No. Yeah, when the exponent is 0, that the x minus 2 is 0 when x equals 2. So you pick the curve for which, when x equals 2, the curve goes through 0.
Yeah,
and all the other 3 distractors, when x equals 2, the curve does not go through the y equals 0 line.
So you know what I did, Seth, is I actually did, but this would go over the exponent rules. I actually tried to do 2 to the x minus 2 minus 1. What is that? That's 2 to the x times 2 to the minus 2 minus 1. So this is 2 to the x, and 2 to the minus 2 is basically 2 squared. Right, a quarter. So this, and when x is 0, because I like to do x is 0 in an exponent, this is 1 over 4 minus 1, which is -3/4. So that means that this graph of x minus 2 has the point 0, -3/4. Choice A is the only one that has a point that goes through 0, -3/4.
Okay, that's the fourth approach.
Now there's the last approach, which Seth suggests. Not, who knows, one of another one. I like the way Seth talked about the asymptotic behavior of the function. What is an asymptote? An asymptote is when for large x, for large dependent variable, for large independent variable x, either positive or negative, what happens to the function? Here, when x is very small, for large,
in other words,
x,
very, 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 very negative.
Very negative. Sorry. You're right. Very, very negative.
Which means very small.
Yeah, okay, very negative.
But its absolute value is very big.
Seth was saying when x is very negative, 2 to the x minus 1, when x is very negative, this thing really goes to 0. So the asymptotic behavior when x is very negative has to be -1. So this is the only one that has that. And this part C, question part C on answer C is the only other one that suggests that when x is negative or largely negative, the asymptote is -1. So the answer is either A or C. And then I
Yeah.
guess you have to use our other you have to use some other approach to choose between A or C, which is one of the other approaches we went over.
Yeah.
So yeah, there's a lot in this problem, right? There's if you want to know, you have to just if you do it this way, you got to know the exponent rules. There's the transformations of functions thing. There's the asymptotes that are helpful. So there's a lot of stuff in this problem.
So it's nothing. I say it's not a lot of stuff needed to solve the problem, but
Yeah.
there are many different approaches to the same problem.
Now, don't forget, people will have access to Desmos, and therefore you can graph two. If you're not sure how to graph 2 to the x minus 1, this thing, you throw it in Desmos, it'll show you what it is, and then you can use the transformation. You could use the transformation approach.
Yeah.
But it's also really helpful to know how to graph simple exponential functions. And notice.
Well,
that,
the thing is if one of these methods we gave you, I think you could get a picture in your mind, and then select the answer much quicker than to bring up the calculator.
I think so. Let's go over again how to graph 2 to the x minus 1. There's this whole thing about parent functions. I know I certainly, when I in school in the 70s, we never really talked about parent functions or transformations of functions. Never did. But there's this whole thing about the parent function here. The parent function of this function is 2 to the x. And they're good. Very important to know how to graph a function a to the x. It goes like this, where this point is 0, 1, 0, 1. And then if it's a -1, you bring the thing down 1 because the -1, if you have f of x, and then you have f of x, f of x is, let's say you have f of x, right? And then you have f of x minus a, the new function f of x, if g of x is f of x minus a, that brings the function down a vertical shift of minus a. So it will go down 1, and this is the parent function.
Okay.
This is the base. This is the graph. So,
yeah. So here's what's weird.
Yeah.
Here's what's weird.
What's weird?
Here's what's weird.
Yeah.
You suppose your parent function is, let's say, y equals parent of x. Okay, that's the parent function. If you give us a new function, y equal, and here's the function. Let's say the function is, it's like that, right?
Right.
And there's the x-axis.
Okay.
And there's the y-axis. Okay. Let me undo this. Let me make straight lines. Yeah. There's the x-axis, and here's the y-axis. Okay. If you write this, parent function of x minus 3. It shifts this one, let's call this y1, it shifts it to the right.
Yeah, we already went to that.
But what is weird? y2 is the parent function minus 3. The other shift is down.
Right.
In other words, towards you go to smaller values of y when you subtract the 3. Right. But you move the curve to larger values of x when you subtract the 3 from the x.
Yeah.
So subtracting to move the curve horizontally moves it to larger numbers on the axis, but subtracting vertically moves it to smaller numbers on the axis.
Yes. Yeah.
It's opposite.
It certainly is.
So that's why it feels weird, and that's why I think one mnemonic I use is that in this case, it's opposite. It's a little weird.
I totally agree. It's for someone like me who gets my left and right confused. I get it wrong a decent amount of time. We are not going to go through the full explanation of transformations of functions, but at its absolute worst, you could have a function f of x, and then you can change it to g of x with a leading a, f of a c in front of the x minus d, plus the b at the end. Well, I'm not sure how many people have done this in Algebra 2, but that is the full, every single one of these, the A, B, C, D does a different thing. We went B, so B, the B on the outside is the minus 3. This uses the B. This one here uses the D. The one with the horizontal shift is the horizontal shift is the D. The vertical shift is the B. The A makes it more slopey, or maybe there's a negative sign.
The A changes the vertical scale.
The vertical scale.
It stretches it out vertically. It's like like that.
And the C is horizontal.
Okay, for small c, let's see. For big C, it's going to squish it together. Right.
We really see that.
So it's opposite again. For big A stretches it out vertically.
Right. Makes it go faster. Everything goes faster.
Big C squishes it together horizontally.
I have to go to the sine curve to figure that out. We know sine of x. And then what is sine of 5x?
Yeah.
Sine of 5x makes it go faster, right? Like that, right?
Yeah.
So a big C squishes it, right? Exactly. Oh, yeah. Let's. So what I do is hopefully it would be helpful to just remember. It's very sort of remember what happens with the sine curve, because it's very intuitive. So you have the sine of x, which is very pretty. Everyone loves the sine function. It's very pretty.
No,
and then you have the sine of 5x. Well, sine of 5x for the same period goes really fast.
It multiplies the frequency by 5.
Yeah, it has more energy, and it's faster. So it squishes, right? It takes this thing here and squishes it so that it's only like.
Well, it squishes the horizontal axis.
Squishes the horizontal axis,
which makes it, as you said, more. Yeah, but
yeah,
both of them, large C and large A, make the curve more slopey.
Yes. Right. Yeah. Right. That's right.
But so pulling it out vertically increases the slope.
Yes.
And squishing it horizontally.
Yeah.
Doesn't increase the height, but it increases the slope.
Right. Yeah. So these are good things to think about. These are good things to sort of, when you're learning this stuff, it's good to have some. It develops the intuition.
Yeah. Well, also, this is what you're going to learn in calculus.
Yeah, but we're not doing calculus. So actually, this sign.
Both the C in here and the A outside have the effect of multiplying the derivative.
Okay, we're not going to
by both C and by A.
Right. We're not.
And the derivative is a slope. I have to say that. I'm sorry, Joel. You don't want to hear from many calculus, but some of our listeners are going to learn some calculus.
Yes, they are.
So we might as well introduce them to calculus a little.
Fine. Okay, calculus is great, because what makes calculus amazing is that at the end, it's extremely powerful, and it's fairly easy to do, fairly easy to use. That's what's great about calculus. Plus,
it's also fair. It also explains all the stuff we're doing here.
Right.
Makes what we're doing here a lot easier.
But why is calculus such a big deal? Because calculus is really the mathematical study. Seth, correct me if I'm wrong. Because Seth, by the way, forgot to say, Seth is a PhD in math, so he actually knows something about calculus. I only have a PhD. I don't want to say that. I have a PhD in mechanical engineering, so I know how to use calculus. Seth understands it more. But let me just quickly say, calculus is such a big deal. We always hear calculus, 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 because in the world things change. We live in a world where things are always changing. Even a steel beam is changing to a certain extent.
Yeah.
And calculus is really the study, gives us the mathematical tools of study how things change. And because in nature virtually everything changes, calculus gives us the tools on how
Yeah.
to
Well,
change.
aren't we studying how things change in a problem like this? We're studying when as X changes.
Of course. Of course.
As X
Yeah.
changes, we are studying the value of this function of X
Right.
changes.
But you
Right.
live
So
your
we are actually doing calculus.
right.
And
Okay.
so I also want to tell everybody in the world that calculus is not, it's not such a big deal. It's not really that hard.
No, it's not.
That calculus follows easily. It's just taking just a few more baby steps beyond this algebra and graphing and graphing Cartesian geometry that you're studying on the SAT.
Right. Right.
When you actually do study calculus, you'll find that it's not. It basically goes over the same things you're doing before calculus,
Right.
but you're talking about it in a slightly different way.
Yeah. What's nice about calculus is that it's a class that's actually on one subject. When you're in pre-calculus algebra 2, it's hodgepodge. You do probability, then you do trigonometry, then you do graphing rational functions. You're all over the place in those classes. Calculus is more organized. You're really very organized. You're not all over the place like in these other classes. I think we're done, aren't we?
Yeah, we're done.
Yeah, we are.
Okay, so let's see their opinion.
Oh yeah, oh my God, we haven't even done that. So let's try to do that quickly. How do they do it? They probably do transformations of functions, but let us see. It's always nice to see. I wish they would do more than one approach. But hopefully that's something that we're offering is more than one approach, although our videos tend to be a little long. But everyone is more than welcome to turn them off as needed, as they feel like. Okay, good. It's always nice encouragement there. Okay, hey, this time they didn't say to click at a. Oh well, this time they one click gives us the answers. Okay, here we go. Let's get bigger. Okay, we need to figure out what the graph of f of x looks like. Notice that doing the problem from the beginning, I sort of started at the end. Like if you know something about transformational functions. Anyway, I started at the end. They started at the beginning. Okay, and then determine how this transforms the function. Don't forget, when I said, let's see how f of x minus 2 transforms the function, and then let's get f of x. Okay, there we go. See that? They're giving us the rules for transformations of functions, right?
No, they aren't.
Yes, they are.
No, not for the wait.
Right.
In part 1/4, they're telling us about that general exponential plus constant form.
Right. Well, that's the sort of unnecessary.
It's also incomplete.
Okay, well, okay. That's a little confusing. C tells us the value is y. So C is basically the asymptotic behavior. Wish they would have said that.
C is the asymptotic value.
Right.
The asymptotic behavior depends on whether B is positive. It depends on whether B is greater than 1 or less than 1.
And X is positive or negative. Oh no, X is positive. That's what you mean by the yes. You're right. Yeah, X is the independent variable. Right. Yeah, it depends on the Ooh, they weren't actually correct.
The rules they give are not complete. You have to know more. Yeah, there are more detailed rules that you have to apply to.
Now, okay, now here's they get to the thing. Here they let's just skipping part 2 for a second. Let's just cheat and look at part 3. I'm like, what is this? A table? Are you kidding me? Anyone seriously going to do a table like that on the SAT? Anyway, they say in part 3, question 3, they say the graph is shifted to the right by 2 units. The table modality is really not necessary in this problem. So we can sketch the graph here, which matches.
Well, what they did, the table demonstrates the statement that they put in the first sentence.
Yeah, but they should have put parentheses. Like, there's no just this table is for information only. You would never actually do it on the test.
Yeah, you wouldn't use it. You would not. No, do not write a table like that.
No, I like that. Believe
when you're on the SAT.
Right, it's got to be like 0% of the people did it that way.
I don't know about how many people would do it that way, but don't be one of those people who do it that way.
Now we just jumped ahead to part 3. Let's go back to part 2. So here they're actually graphing the function. Wait, no, that's not the function. Oh, that's the function. Yeah, that's the function 2 to the x minus 1.
Yeah.
It's interesting that they didn't do it using transformations of functions. They didn't do it graphing y is equal 2 to the x, which is this one, minus 1 blows the thing down 1 unit, right?
Right. They didn't say that.
They went directly. Well, feel free on Desmos just to unograph it directly. So this takes a little bit more. This is basically using a table. To a certain extent, this is using a table, right? Because they're making a table. X, Y. X 0. Y is 0. As X is greater than 1, Y increases towards positive. So if X is 300, then Y basically goes to infinity. Right? So they're essentially using a table to graph this. Maybe it's better, if you're going to do this type of logic, it may be better just to use Desmos, which they're going to give you on the digital SAT. So,
well, okay. I say it's best. It's best. Let's see, they used a B. It's best.
Best.
That you recognize that an exponential function like this, when there's an exponent, right? And we're talking about a positive exponent.
Sure.
The positive exponent. And when the key thing about positive exponent curves is that when x is b to the x, let's plot b to the x. When x equals 0, b to the x is b to the 0, which means you're multiplying b by itself 0 times, and it's 1.
Right.
No matter what b is.
Yeah.
And then, so b to the x minus 1 is plotted by pushing it down by 1.
Right. Yeah.
So no matter what b is, as long as it makes sense, or b is where b to the x minus 1 always goes through the point 0, 0.
Absolutely. Right.
Yeah. And then the question is, does it look like this?
Right.
Or does it look like this? Oh, no. Or does it look like this? Right. In both cases, and whether it looks like this when b is greater than 1.
Right.
And it looks like this when still greater than 0 is less than 1.
Right. So in other words, a normal looking fraction.
Yeah.
Normal.
If b is negative, this gives us problems when x is negative. We get complex values. You get if b is negative. For many values of x, it's undefined in the math of the SAT.
Yeah, so no one's going to say.
Right? And when b is 0, let's see the intermediate step. F of x when b is 0 is 0 to the x minus 1.
Yeah,
and there's a convention that no matter what x is, 0 to the x is considered to be equal to 1.
Really?
Yeah. So
you're kidding. Wait. Are you telling me that 0 squared is equal to 1? No. How could that possibly be? What are you talking about? How could that rule be 0 squared is 1? That's impossible. What are you talking about?
Oh, no, I'm sorry.
Yeah.
No, absolutely wrong. Completely wrong.
Of course you're wrong.
Nah, what am I saying? When b to the x. Okay, I'm kind of floundering. So here we go. Let me redo. F of x, again, we're working with b to the x minus 1. When x equals 0, b to the 0, the convention is no matter what b is, when b raised to the 0th power by convention is equal to 1.
That's right. Yeah.
So independent, no matter what x is, we're going to go through to this point.
Right.
And then the issue is, how does the curve look? How does it vary for different values of b?
Yeah, but we've already done that already. So you know what?
We've done that. Now, what if b is negative?
Well, can I erase this for a second?
Yeah. Go erase
anything. Yeah, but okay, yeah. Let's just look at some. We're in trouble, right?
We're in trouble. If b is negative, we're in trouble. Yeah.
You have -3 to the -1/2 power. You got a problem here because you're doing even the positive 1/2 power, right? You're
doing the square root of -3
minus 1. That would be interesting to put it to Desmos, right?
Yeah.
That would be interesting. But you're saying...
Well, the problem is, what's the problem with the square root of -3?
It's complex. It's an imaginary answer.
Well, from the point, the point of view of the SAT.
The square root of 3i.
The square root of 3. The square root of 3 is supposed to be a number.
Yeah.
Right, a number. That when you square it, you get -3.
This is equal to -1 plus radical 3i.
Okay, don't give me this radical business. A number which when you square it, you get -3.
Right, okay, yeah.
Now, do you know any numbers that when you square them, you get a negative number?
Of course not. It's complex. Why are you beating around the bush? The answer is complex.
Well, what if you didn't know? What if you didn't invent complex numbers? What if you had ordinary numbers?
That's an interesting point. I'm not sure.
Why do you need complex numbers in the first place?
Look, I don't know.
The reason is there ain't no numbers.
Right.
There ain't no ordinary real numbers with a property that when they're non-zero, you square them, you get a negative number.
Right. Okay.
So if your math does not include something extra that has been added to the number system, there's no number whose square is negative.
Right.
Right? So so you can't plot it. It's just it doesn't there isn't anything that any numerical value for the square root of -3 or even the square root of -1. However, now we talk about complex. What happened complex? Not all that long ago, maybe in the 1700s. In the 1700s, mathematicians had the idea that maybe we could invent a magic numbers that are called imaginary numbers
Yeah.
to make up the lack of numbers whose square is negative.
Hmm.
So that's why that's so. So what they did was, and the man was called the Prince of Mathematicians, Carl Friedrich Gauss,
Yeah.
realized that you can make sense. You can do mathematics. In other words, you could do do mathematical type problems that are logical and make sense if you invent additional numbers, which they called imaginary numbers,
Right.
with the so that you so when you square them, you do get negative. Yeah. So then they said, what happens if you add an imaginary number with a real number?
Yeah.
Again, it's still it's not a real number. So they gave the name complex for those numbers that are so-called pure imaginary, plus some non-zero real.
Hmm.
So the thing is, what they did was invent complex numbers so that every quadratic equation
Okay. Yeah.
has solutions.
Okay, Seth. So let's get back to this. How? What did I do? Did I just blow the brains out of Desmos? I'm trying to graph y is negative things. By the way, this is what you should do. You can have fun with math, right? This is a good time to ask Seth. Feed the Seth. Did I just blow Desmos out of its brains? I'm trying to graph -3 to the negative x plus 1, and look, it doesn't
Yeah.
graph it. But when
What
x
is it
is like,
doing?
but when x is like -3, there's like there's an answer to that. When x is
Well,
-3,
it
negative.
didn't plot anything.
I know. So what do you think is going on? I mean, there were
Well,
some, there were some, there were when I did it, there were some little points that came up. Let's see, -3 up to the negative x. See, there's a dot. See how it came up with the dot?
oh
Plus
yeah.
a plus
Okay,
plus
when
plus
x
two.
is zero,
Yeah, see, it came up with a
when
dot.
x is zero,
Came up with a dot.
when x is zero, it makes sense.
But you're saying that doesn't make sense when x is not zero.
When x is uh when x is one, it makes sense.
Yeah, but how come it didn't graph x is 1?
But what if x is equal to 1/2?
No, it doesn't make sense. So why didn't Desmos at least put some? Anyway, Desmos didn't graph it.
It's not perfect.
What do you mean it's not perfect? Perfect is not a mathematical term for this, is it?
It doesn't do the math. Desmos fails. It's what it should do
Yeah.
is plot. It should plot the points for the x's for which it does make sense and show them.
Oh,
But it didn't do that.
let's do a competitor graphing calculator. Okay, Mathway.
Yeah,
Okay,
okay.
let's see Mathway is a what is this? I love parentheses. -3 to the negative x plus 1 doesn't matter. So it's not doing it either. Okay. How about this one? Y is equal to 3x. Okay, y is equal to 3x. It says there's no problem with that. Ooh, look at that. Doesn't work either on Mathway.
Yeah. Well, maybe
Wow.
they put in the same code.
Yeah, maybe they use the same code. Yeah.
Yeah.
Yeah. Anyway, so we looks like we stumped math. We stumped. Yeah, but I don't know. Wait, I don't even. I stuffed them all to mathematics PhD thing.
Yeah.
What do you do? I don't know what to do. In the end, obviously, you didn't get anything like this on the SAT. But that's interesting, right? I never even thought about that. So it's good to think about things, even if you're way above your level. So have you ever thought about that? How do you graph that?
Well, I could think about it now.
God. batten
it's
down the
it
hatches if Seth's thinking about something now.
yeah, it's you know, first of all, it does make sense. It does make sense to extend the domain into the complex numbers.
Yeah,
The
okay.
trouble is the grapher only graphs real numbers.
Right, yeah, okay, that's a good
So
excuse.
if a point is complex, it doesn't have any way to graph it. So it
Right.
shouldn't show it.
Hmm. Yeah. So
Yeah.
there are an infinite number of points for which this will work, and there's also an infinite number of points for which this will not work.
Yeah.
Is that
Yeah.
correct? I don't know what I'm talking about because I only have
Well, could you give it a range over, say, which x you want to plot it
well,
for?
okay, here. For example, like for x is equal to 7/2, I don't think it works. Right?
Yeah.
X for 7/2 I don't think works. But for
Uh,
x is equal to 4, it works. Or for x is equal to 4 and 4/5. No, I didn't even know. 4/5? -3 to the 5th? What's the 5th root of -3? No, let's say the cube root, that would work, right? 4 and 4/3, which would be 5 and a third. That would work, right? If x is 5 and a third, that would work. There's a negative root for, there's a negative cube root for
wait, I
-3.
don't know.
So if x is 5 and a third, it works, but if x is 7/2, it doesn't. So I don't know. I don't know. Anyway, Thomas, we are so above everyone's
Okay.
level. We better stop. We really better stop. We really better stop. So anyway,
What if you type in
okay, go ahead.
just calculate -3 to the minus a half.
Minus
Give it an
3
arithmetic problem.
up to the minus 0.5.
Yeah.
Okay. No, it doesn't say but the answer. But let's do -3 to the half.
It has a red. What's that red spot?
Wait. Let's do to the half. Oh, I don't know.
It's asking. Yeah. What if you press enter?
I am. Yeah.
I
am. I don't know.
What if you say -3? What if you say 3 to the 0.5?
Okay.
0.03 to the 0.5.
Just 3 up to the 0.5. It's like 1 point. Yeah. Oh. Yeah, that's it. Y is equal to 3 to the half.
Oh, I see. It's plotting. All it's doing is plotting.
Yeah, but it's saying is y is equal to.
Yeah.
It's saying y is equal to 3 to the half.
Yeah.
So why do we say y is equal to
the fifth to half? That's the square root of 3.
What did you say?
It's about 1.7.
You said -3 up to the half.
Yeah.
There actually is a square root of negative. Oh no, there is no square root of -3, but there is a cube root of -3.
Mm-mm.
I don't know. -3 up to the 1/3. 1/3. There it is. See, that worked, right? See that?
Yeah.
That worked, right? Or even to the third, right? Yeah. See, that worked. That worked. That graph. That gave you that gave you the answer. Right? But it just doesn't work for a half. Right?
Yeah. So that. So
it just doesn't work. Yeah.
-3 to the third is the number which, when you multiply it by itself 3 times, you get -3.
Right. It's the cube root of -3.
So it's the cube root of 3.
Yeah.
Times -1. If you multiply -1 by itself an odd number of times,
what
do you get?
A negative number.
You get -1.
Yeah. Yeah.
If you multiply -1 an even number of times by itself,
You
what
get
do you get?
positive one. You get positive one. Yeah.
So there's no way you could multiply
Right.
-1 by itself an even number of
Right.
times
So
and
the
get a
so
negative number.
the bottom line is these things only work for real.
Yeah,
The domain for Mathway and Desmos seems to only
yeah,
be real functions giving
yeah.
real solution, real answers. That's probably why this one simply fails because there's some complex stuff, so it just
Yeah.
says I give up.
Yeah.
So
Well, so they ought to make it print a message
yeah, yeah,
that says some of the values to be
yeah.
plotted don't exist.
We used to, the show, the Twilight Zone. You've entered the Twilight Zone. Here they could say, you've entered the complex plane.
You're asking me to for something that asking me for the impossible.
Right. Yeah, 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 yeah. Okay,
Yeah.
now we are really
But it
right.
really should say it's impossible with a real
Yeah.
plotter.
So what did Seth and I do? What approach have we just played with the last 20 minutes? We had a question. We were wondering. We played around with it. A good approach
Yeah.
with math is just take a chance. You have these Desmos tools. I mean, Seth and I obviously never had these things when we were high school kids that have a graphic calculator, have barely a four function calculator, let alone anything to actually play around like
I
this.
had no calculator at all. I had
Seth has no
a slide
calculator
rule.
rules, right? So that yeah, so it's fun to just
And
around
my
with.
grandparents had an adding machine.
Yeah, but they had slide rules in the days of your grandparents, but they may not have had the
Oh yeah,
cash to buy one. They may not have, or the interest, or the need to buy a slide rule because they
yeah,
weren't doing a lot of multiplication or division, but they were adding stuff.
yeah.
So, okay, we are
Okay,
seriously done.
we're
So,
way over.
we are
Yeah.
really way over. So, I assume
Okay,
nobody is
overtime.
left. Yeah, like,
We're going into overtime.
we're beyond overtime. Okay, everyone, have a great day. I hope you got something out of this. At least learning how do we approach things. How are we thinking? That's a little big takeaway. Okay, bye bye. See you later,
Bye
everyone. Like
bye.
us, dislike us, give us comments. We love comments. We sort of appreciate the comments, so we have feedback. Okay, everyone, have a great day. Bye.